All right, well, good morning, everybody. People who are online, people who are here in the room with me. It's very nice to see you folks, and it's very nice to see at least you folks' number online, I guess. So do say hi in the Top Hat chat if you like, but I've also posted a question just to get us starting thinking and remembering things. And you know what? I'm gonna have to just move that tab somewhere different. Yes, I have put the question up now, and now hopefully everybody should be able to see it, those who are online and those who are in the room. So there's a question for us to answer. Just thinking back to what we've been learning about new data structures, which include dictionaries and sets, which are very exciting and cool data structures that let us do neat things that are harder to do with things like lists. So hopefully people are able to see that online. I would ask you to type in the chat whether or not you can see it, but there are two problems with that. One, Top Hat still hasn't fixed their chat, so that's really annoying. I did create a pseudo chat question that you can type in, but maybe you can't while the question here is active. So I'm just going to have to look at the number of people who are answering and see that going up. Yeah, so this is a moment where I would like to fill the space while people are answering by asking, how's everybody doing this morning on this beautiful day? But that's a little tricky because the chat is not visible. So I'll just give us a few more seconds to answer this question. What's going to happen here? All right, I'll give us just a few more seconds and I'll close this question out. And we'll see how everyone did with it. So let's give this another 5, 4, 3, 2, 1, and we'll close it. Okay, so what will this code print? Let's take a look at what people thought. Okay, so mostly people thought either C or 3, and there are a few other options that came in. Okay, so the key thing to remember here, there's a little pun. When we I didn't mean it, I'm sorry, I'm just so full of puns that they just come spilling out of me. Yeah, so when we iterate over a dictionary, by default, we can specify that we can iterate over the keys using the keys method, or iterate over the values using the values method, or iterate over all the items using the items method. But by default, what do we iterate over? Keys, that's right. And probably somebody typed that in the chat. So that means if we're iterating over the keys in this dictionary, we're iterating over A, B, and C, and then the max value there is C. Very good. Okay, now let me pop open my chat again so that I can see people saying good morning and such. Yeah, look at that. People saying good morning, hello. Well, it's nice to see everybody. Okay, so let us start talking about something new today. So we have been talking about new data structures. Now we're going to go back and look at something that we've been talking about, well, since almost maybe in fact the very first day of this semester. And I said, well, let's use integers. And later in the semester, I'll come back and explain how a computer actually represents these integers. And this is kind of a very, very common thing that you'll see in an engineering program where there's this spiral of learning. Well, we'll introduce a topic, and then you'll come back to it eventually, and you'll either see it at a lower, deeper, more fundamental level and keep drilling down as you understand things in greater and greater depth, or sometimes you'll see something and then you'll come back and build on it and build on it and build on it until you can build bigger and more complex and interesting systems using the idea that you may have been introduced to very, very early. So there is a sense in which, having been introduced to programming in this course, somebody can say, do you know how to program in Python? You can say, yes, yes, I know how to program in Python. And then there's another sense in which you can go kind of deeper and say, well, I'm proficient in Python programming. Or you can go to an even deeper level, and there's no limit to how many levels you can go to in terms of, there's always another level to level up to, something like that. It's kind of like, I play the piano, but I have friends who play the piano a lot better than I do. But, there's always a deeper place to go. So that's where some of those musical analogies come from. And so similarly, this is one of these things where we've introduced a concept, but now we're going to look at it in a little bit more detail. And hopefully this will be really satisfying, because you'll be able to say, oh, now I actually understand how these things work that I've been using all semester long. Someone says, what are the quizzes shown on Top Hat? Yeah, that's a good question. So people were asking for additional kind of practice questions, that kind of thing, to prepare for final exam and thinking about stuff. So in Top Hat, I have posted some quizzes that are not really quizzes. These are just going to be exercises. Oh, there I am out in the room as well. So I've posted some Top Hat quizzes, which actually were real quizzes last year when everything had to be completely online and there was no in-person evaluation. We did these online quizzes. Now then, they were set up with a little bit of remote proctoring and stuff. But right now, I'm just giving you those questions so you can use them to practice with them. And I'll treat them just like all the other Top Hat exercises, which means that you should do them, and in fact, there's a score for doing them, and there's even like a half a point or something per correct answer. But like all the other Top Hat exercises, you can do them with others. Now, I would suggest it'd be a good idea to at least challenge yourself to try to do these things yourself, and maybe try to do the question yourself in a test-like scenario where you don't have access to a Python interpreter or the course website or things like that. See how you do with that. But then if you want to talk about your answers with your friends before you submit the final one, that's totally fine. Exercises are you're completely free to work together. Assignments are individual work. Do not collaborate on assignment work, but the exercises, feel free to collaborate as much as you like. So hopefully that helps. Someone says, what was the average on the midterm? I think that went out in an email, so you should have gotten that. I mean, it was out of 50, so multiply by 2. Pardon? 62, someone is saying. Okay. There's always a bigger fish. Oh, I guess that's in reference to my comment about you can always go deeper. Yes, and the deeper you go, the bigger the fish you find. I'm not sure. Maybe there's a metaphor there somewhere. But let's not bother trying to figure out what it would be right now. Today, let's talk about integers. Okay. So we have talked about how to store things in memory. So how do we store things in a computer's memory when we're programming? Right, so an assignment statement, and that will assign a value to a what? To a good morning. No, the chat is slightly out of sync. There we go. Sorry? Right, so it'll store it in a variable. So an assignment statement takes a value, puts it in a variable. Okay, so that's good. We've said that values can be stored in variables. And variables are places in memory that hold values, and they're places that have names associated with them. So we can have a little box, and let me see how smoothly I can switch back and forth and on my little simulated, not quite a whiteboard. So we can have places in a computer's memory where we say, well, this is a box that I'm going to call X, and this is a box that I'm going to call Y, and maybe we initialized X with the value 4 and Y with the number 2, and then we wrote some code and said, okay, X is going to be assigned by Y divided by 3 with 2 slashes. All right, what's this going to do? All right, so we're going to take the value of Y, we're going to look up that value of Y, and what is the value of Y currently? It's 2. So 2 /3. So in integer math, what is 2 divided by 3? I heard somebody say 0. That's right. So it's 0 remainder, oops, not 1. It's 0 remainder 2, which means this value 0. So this expression, Y, integer divided by 3, that evaluates to 0. And so that number 0 goes into x. So x used to be 4, now it's not anymore. Now it's equal to, or now it holds the value 0. So we've said that variables are places that you can store values in a computer's memory. We talked about different types of values that we can store in that computer's memory: an integer, a Boolean value, a floating point value. And in fact, next time we'll talk about how floating point numbers are represented. But guess what? They're actually represented using integers. So a computer knows how to store integers, and it can put integers together in different ways for different purposes. But an integer is an integer. A Boolean value is just an integer that's stored as either a 0 or a 1. A floating point value is in fact a collection of integers that are used in a particular way, a mantissa and an exponent. We'll talk all about that next time. But in fact, we can store floating point values using integers. It's almost like it's not quite the same thing as rational numbers, but you can represent rational numbers using integers. And for any real number that you want, you could get pretty close to that real number using a rational number. So the division of two integers, well, that's a way that you could imagine represent. It's not quite what we do, but we'll talk about that on Wednesday. But you can see how you could use two integers to represent a floating point value. What's a string? Oh, we've got a new hi in the chat. Hi. So what's a string? There we go. Somebody is reading off the slides, and that's good. That's good. We're paying attention. So a string is a collection of characters, and we've seen that each of those characters can be represented with an ordinal number. So in fact, strings are just collection of characters, and characters are in fact represented in the computer's memory as integers. So it turns out that computers are really, really good at storing integers and then doing mathematical operations on them really quickly. Computers are not clever, computers are really dumb, but they're really fast, and they can do integer operations extremely fast, like billions of times per second fast. All right, so we've talked about variables, and we've talked about values that can be stored in them, but we kind of weren't very clear about how that works. Well, now we can see that a lot of stuff is going to depend on how we store integers, how a computer actually represents an integer value in its memory. And so we're going to talk about that today. And then we'll really understand in a much deeper way how computers actually work and what they're doing. Morning in the chat. Morning. Okay, so how do we store those integers? So one thing that we need to know about variables, in addition to what we've seen so far, we've seen that variables have names, right? So I'm naming this variable x, and I'm naming that variable y. Well, not only do variables have names, variables also have places that we store them in memory called addresses. So much like you could say, well, where is your office? And I'd say, well, it's on, actually that's probably a bad example because there aren't a lot of buildings of interest on Arctic Avenue in front of me. But if it was on Bond Street downtown, good evening, Mr. Bond. Sorry. If it were on Bond Street downtown, then I might say, well, my address is at number 3 Bond Street, or number 27 Bond Street. There are a couple of tech companies down there. So I might have to give you the address, which is just a number that indicates where to find something on a particular street. Well, a computer has memory, and we can think of that memory as just a huge, long line of places to put bytes, 8-bit chunks, 8-bit numbers. And starting at the number 0 and going up to the number, in the case of this computer, 16 billion or so, that's a large number of places that I can put values. And each of those locations in the memory has an address. And so we can actually find out in a lot of cases what the address of a Python value is. Oh, sorry, I'm getting slightly out of order. I'm so excited about all this stuff that I keep getting ahead of myself. Right, so variables have names, they have addresses, which we can find out what they are. Actually, no, I'm not getting ahead of myself. This is exactly where I planned to say this. So don't worry, folks, I am a professional. Sometimes. Okay, let me bring Thawny up here. So using an assignment statement, like we said earlier, x equals 4, y equals 2, and then maybe let's view variables. And let's say x is assigned by y, integer divided by 3. So now things look kind of like they did in our little example earlier. We can look at the value of x by just typing x, look at the value of y by typing y. We can find out what is the type of the value stored in x. It's an integer. What's the type of the value stored in y? Well, it's an integer. We can also use a function called id, and this is something that we're not going to need to use. This is just kind of illustrating things for you. But we can use a function called id to ask Python, can you give me a unique identifier for this specific variable? What is a name that is meaningful for the computer for this variable? Because the name x is just for programmers, right? That's a convenient thing for us, but the computer doesn't care whether I call this variable x or y or late for dinner. The computer really doesn't care what I call this variable, but this is a name that's meaningful to the computer, and it's a number. And it turns out that in pretty much all implementations of Python, that ID that you get is actually an address in the computer's memory. And so that is a location that says if you were to go to the address 4,365,609,728 at that location in the computer's memory, you would find this variable that the programmer is calling x. Because isn't x a whole lot more convenient to say than 4,365,609,728? Or if I wanted to then talk about the variables x and y, well, I'd really hate to say the variable at 4,365,609,728 is assigned by the variable at 4,365,309,792 divided by 3. Right? That would be really, really awkward. I'd rather say x is assigned by y divided by 3. Okay, and so that ID function can actually tell us where the address of that variable is. Now, if you try this at home, and do try this at home, there may be circumstances in which you see numbers that are so big, they are bigger than your computer's memory. And you might say, whoa, how is that possible? Well, the answer is a little something called virtual memory, which, if you go into computer architecture in like term 6, you learn how all that stuff works, and it's pretty cool. But for now, just know that there is an address, and it's going to be a really big number. But how does the computer actually represent the value that's stored in that location? So, remember on day 1, I told you that a computer has 3 major parts that matter. There's a CPU, which does what? It computes things. So if you want to know, dear computer, what is 1 plus 1? The CPU has a little chunk of it called the arithmetic and logic unit that is going to take the 1 and add them together and tell you that that's 2. Or we can also do slightly more impressive things with larger numbers. There's a CPU, there's I/O, which stands for input and output. That's right. So I have a keyboard that's taking input. I have a trackpad that's taking input. I have a screen that is giving output. I have a network card that is giving input and output back and forth to Top Hat servers and back and forth to YouTube servers. So we've got lots of input and output that's happening, but also we have the computer's memory where we store stuff. Now, does this look familiar to anybody? Yeah? Okay, cool. So some folks have built a computer, or at least taken a computer open. Maybe you've upgraded your memory. Maybe you've built a computer from scratch. Maybe you have broken a computer and then you've seen what's inside. The files are in the computer. Sorry, maybe that's a little dated a reference. I don't know. Do the kids today still watch Zoolander? Maybe not. All right. This is kind of a fun picture. So this is memory from fairly recently in the form of a micro SD card, like you might put in a phone or a camera or a Nintendo Switch. And also some memory that was manufactured 50 years earlier. So you'll see here there's an SD card, and it's sitting on top of this little grid of little metal rings. So those little metal rings, each one of them and this was kind of like state-of-the-art stuff in the late 1960s, early 1970s. Each little ring could be magnetized by these wires, and it could represent a 1 or a 0 based on its magnetic state. And you could use these electrical wires to change the magnetic state of the rings, and you could use the electrical wires to read the state. So you could read a 1 or a 0 from each one of these. And so how many 1s or 0s could be stored on this magnetic core memory that is sitting behind the SD card? Count them. So let me see if I come over to here. I'll make this picture bigger. Maybe that'll help. All right, answers are coming in. Now I'm just talking about, just to be clear, the square here behind the SD card. So I'm ignoring these bits over there and these bits over there. So we're only talking about this square of metal rings behind the SD card. All right, I'm going to close this out in about 5, 4, 3, 2, 1, and close it. Okay, and now let's have a look at the answers. Okay, yeah, so most people had it right, which is 64. If you count here, we've got 1, 2, 3, 4, 5, 6, 7, 8 rows, each of which has 1, 2, 3, 4, 5, 6, 7, 8 columns, which means that chunk of magnetic core memory, which is about this big, could store 64 bits, 64 zeros or ones. Now, there are 8 bits in a byte, B-Y-T-E, which means that this SD card could store about 1 billion times as much information as that chunk of physical magnetic core memory could store. So in 50 years, we went from this size of a thing being able to store 8 bytes to this size of a thing being able to store 8 gigabytes. Or, you know, these days you'll buy an SD card that size and store 128 gigabytes. No problem. So we've come a long way in terms of how much stuff we can store in a computer's memory. And the way these things work has changed immensely. We no longer have little metal rings that can be magnetized or demagnetized, etc. However, although the technology used to build the memory has changed greatly, both of these things, the magnetic core memory and the SD card, are kind of doing the same thing. They're storing zeros and ones, and they're persisting them so that even if the computer turns off and back on again, that those values are still in that SD card. Whereas the memory here on the left, this stuff, RAM, random access memory, when you turn the computer off and back on again, once the power gets turned off on these RAM chips, they no longer contain whatever was there before. You turn them on and they contain arbitrary junk in an uninitialized state. So what's in the computer's memory? Well, we've got these bits, and every bit is 0 or 1. And bit is actually a portmanteau of 2 words. It's a binary digit. Does anybody know, by the way, oh, sorry, let me close the question over here so I can see the chat again. Does anybody happen to know, and I have no reason to suspect anybody does in particular, but does anybody happen to know what the SI unit is for information? What is a bit in SI units? So there's grams and meters and all these different SI units that we use, joules, etc. But do you know what the SI unit is for information? So a 0 or a 1 in the SI system is called a Shannon. So it's named after a fellow named Claude Shannon, who's kind of the father of modern information theory. And it turns out that it actually has a relationship to the other SI units. There's a thermodynamic amount of work that gets done by changing a 0 to a 1, which is kind of cool. And actually, people can measure this, like they've exposed mice brains and things and then fed them a certain amount of information via visual stimulus, and you can measure the energy that's being used by the mouse's brain and calculate how efficiently it's processing, which is kind of weird. But right, so a bit is a 0 or a 1. It's on or off. It's true or it's false. 8 bits makes for a byte, and this is kind of where we store most information. A byte can also in some cases be called an octet. Why an octet? Well, because there's 8 bits in a byte. So this hard drive holds 500 gigabytes. My network port in my office at least can run 1 gigabit per second, so I can move 1 billion bits per second in and out of my office. The stream that we are doing right now is using... Sorry, it's in this program. Right now I'm streaming at about 4,000 kilobits per second, so about 4 megabits per second are moving up and down, or moving up from this computer to YouTube servers. So, what's this? You notice I asked the question in a slightly unusual way, which should be a clue that something's going on here. What's this? 1 0. Well, the answer is, like any good academic, I'll say the answer depends. Or it could be yes, or it could be no. So the answer here is, well, it really depends. So when you see the digit 1 followed by the digit 0, you immediately think 10, right? And that works in a base 10 representation of numbers. So typically, when we are writing numbers down, and you'll see lots of numbers written in engineering, and nobody ever bothers to say this is using a base 10 representation. But there is more than one way to represent numbers using digits. So base 10 is, of course, very common, but it's not the only representation. Can anybody think of an example of a vigisimial representation, a base 20 representation of numbers? How about 90? Right? We count how many 20s there are and then add more stuff to it. Which, of course, also got ported into English for a while, right? 4 years ago, that's 4 20s plus 7. And we might say, oh, that sounds crazy and archaic, but this is a kind of live representation of people certainly have, and to some degree still do, count in base 20 systems. And different cultures around the world will have different counting systems. I think there are some places in the world where people still use primarily a base 20 way of representing numbers. There's also base 5, but something we're going to be particularly concerned with in programming is a base 2 representation. Because if you have a decimal representation, what are the values of the digits you can have? What are the digits that we can have in a base 10 representation? 0 to 9, there we go. So in a vigisimial representation, you can have things that mean from 0 up to 19. And then you have, okay, well, that's how many I have in my units, plus how many 20s do I have. So I have a certain number of 20s plus my units. Now, even in French, they don't go all the way and then say, okay, we've got these many units, these many 20s, these many 400s, these many 8,000s. That's not quite how the counting system works, but still, there's a remnant of it there. In computing, we care a lot about being able to count using a base 2 representation. Why? Well, because the things that the computer knows how to represent really well are 0 and 1. So if we treat each digit in a number, or if we use zeros and ones for our digits, we are going to be able to count using a base 2 representation. We also are going to, in some cases, care about a thing called a hexadecimal representation. Hopefully the word hexadecimal is something people have heard. Anyway, that's a base 16 representation, and we use that only because it lines up nicely with a base 2 representation. So how does all this work? Well, let's go back to school. So, our younger son is 6. He's 6.5 actually. So he's finished learning about the place value of numbers, and there's like the ones house and the tens house, and when the ones house is full and the tens house is full, they move together into the 100s house because they need more room, etc., etc. Well, let's do the same thing, but with binary representations. So, the number 12, what does that mean? Well, first of all, in a base 10 representation, how do I write the number 12?
1 10 and 2 1.
Right, so it's 1 followed by a 2. So it's 1, 10, and 2 ones. If I had the number 312, then it would be 3 hundreds, 1 10, and 2 ones. And as we change these values, so let's say that we are increasing 313, then we add another one, we get to 314, then we add more and more and more. Eventually we get to 319. Now I want to add one more. How do I do this? And this is stuff where, again, you're like this, I can't believe I'm doing stuff that I did when I was 5 or 6. But there's one of these things where it's so natural to you, it comes as like without a second thought, that we actually have to kind of go back and think about, oh yeah, how did I learn that, so that we can figure out how to do it differently. So 319, now I increment this by 1, what happens? We have 3110. 3110. Yeah, we've got a thumbs up there. Nope, not quite. So we can't store the number 10 in a single digit. So we say 10, well, that means we're going to have to take this 1 and add it to our tens. So we will instead have the number 320. Right? So our different digits start at the lowest, but they start at 0, and then they keep incrementing up until we get to the highest value that that digit can have. And then once we get to one more than that, we need to, it goes back to 0, and we bump the next digit up by 1. Well, let's say that we had a different way of representing numbers. Let's say that we had a ones place. Oh, sorry, the other thing that we had to notice there, what's the difference between each of these place values? All right, so we add another 0. Yep, what does that mean? Right, so in order of magnitude. So each of these is 10 times greater than the previous one, right? So let's say we want to have a base 2 representation. We're still going to have a units place. So we could still have the number 1 in our units place. But now, what's the maximum digit that we can have if we have a base 2 representation? So with a base 10 representation, our digits could go anywhere from 0 to 9. So with a base 2 representation, they're going to go anywhere from 0 to 1. That's right. And now, what will our next place be? It won't be a tens place. It'll be a twos place. And the next will be a fours place. And the next will be an eights place. 16, 32, 64, etc. And so what is the largest number that we could write here using these 7 digits? So if we had 7 digits in a base 10 representation, the largest number we could write would be 9,999,999, right? Repeating the largest digit over and over and over. How about here? So we'd have a 1, a 1, a 1, a 1, a 1, and a 1. So what is that? Well, that is 1 times 1 is 1, 1 times 2 is 2, 1 times 4 is 4, 8, 16, 32, 64. So we would add all of these up. Now, we could do that the hard way, or we could do this the easy way. What is, so if I said the largest base 10 representation, or the largest base 10 number we could write with 7 digits would be 9,999,999. That's 1 less than 10 million, right? So this is 1 less than this, okay? Because if I were to add 1 to this number, so if I want to add 1 to that, well, we would try to increase, in fact, let's do that this way. We try to increase this by 1. Well, it can't be 2, right? So it's going to have to be 0, and then we add 1 here. That's going to want to be 2. Well, we can't do that, so this will become 0, and we add 1 here. Let me write that 0 in a different place so that it's consistent. And we add 1 here. So we're trying to add these two together. We want that to be 2. Well, it can't be, so it's 0. We add 1 here, etc., 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 all the way up until we get to 1, 0, 0, 0, 0. And what is that value? Well, so if this place here was the ones place, and this is the twos place, 4s, 8, 16, 32, 64's place, what's the next place going to be? The 128's place. So that means that this number is 128, and this number, which is 1 less than that, is 127. So if we want to convert a binary number, 1101101111, into a decimal number, one really convenient thing about this representation is that, unlike some other representations, we don't actually have to do any multiplication. So let's imagine for a moment. Let's imagine we were talking about a base 5 representation. And we had a number like 3, 4, 2 in a base 5 representation. How would we compute its value? So first of all, 2 times 1 is 10, 4 times 5 is 20, and 3 times 125 is? Come on, future engineers. Oh, somebody said 127 in the chat about the binary number. Good job. Sorry, what's 3 times 25? All right, 75. Oh, sorry, I said it as 125, didn't I? Right, so 75 plus 20 plus 10 is equal to 95, 105. There we go. So you see we had to do this multiplication first, and then we add up all those values together. In a binary representation, we don't really have to do that multiplication because we have times 1, times 2, times 4, times 16, times 32, times 64, etc. Because all of these numbers are only going to be 0 or 1. So we never actually have to do any multiplication. We only ever have to add the numbers up. So here we have a 64, we don't have a 32, we do have a 16, we do have a 4, and we do have a 1. So if we want to add those up, that would be 80, 84, 85. There we go. So in a base 2 representation, 101101 is 85. Which, by the way, is how we can count digitally. So again, we have 10 digits here. Well, you can actually use these as zeros or ones. So you can count in one hand, what is the largest number I could represent with 5 ones in a binary representation? Yeah, well, from 0 to 31. So I could represent 32 different values, right? So if my finger not touching my palm is a 0 and touching my palm is a 1, then I can count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. And then if I add these digits, so that's all 31, and then here's 32. And so I can actually count to 1,023 using nothing but my hands, which is kind of convenient sometimes. The 6-year-old is not so into that, but the 9-year-old thinks that. That's awesome, which is kind of fun. Yeah, children of professors. What are you going to do? They're going to grow up with a slightly unusual worldview. But they get exposed to cool stuff. So this is how we can use binary numbers to represent integer values. And this is exactly what the computer is doing. So when the computer can only store zeros and ones, what it's actually storing are integer values. So let me ask you this. So let's say we have, and the little 5 there means that this number is written in a base 5 representation. So what is the value of the digits 1, 2, 3, 4 in a decimal, what is the the value of the base 5 number 1, 2, 3, 4? How would we convert that into a decimal number, which is what we're used to working with? While you're answering that, I'll start preparing our answer here. So 1, 2, 3, 4 in a base 5 representation. Which, by the way, I should probably mention is, if we're using a base 5 representation, this digit is whatever that base is to the power of 0. This is the base to the power of 1, base to the power of 2, base to the power of 3, etc. All right, I'm going to close this out now in a couple of seconds. So let's close this question in 5, 4, 3, 2, 1, and we'll stop. Okay, so how do we answer this question? So a base 5 representation, we have a 1's place, 5's place, 25's place, 125's place, so 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3. So we have 4 times 1 is 4, 3 times 5 is not 13. Got a 3 in my brain. 3 times 5 is 15. You folks might need to check my math here. 2 times 25 is 50, and 1 times 125 is 125. So that's going to be equal to 125, 175, 190, 194. So let's see what people said. And yes, most people had 194. Very good. Some different answers there, but 194 was the right one. We can also do this the other way. Let's say that I have a number that I want to represent in a binary representation. So here's my times 1, times 2, times 4, times 8, times 16, times 32. Okay. Let's say I want to represent the number 25 in a binary representation. How could I do that? So, we have a choice. We can kind of work from the smallest place to the largest place, or from the largest place to the smallest place. Let's work with the largest place to the smallest place. We can do it either way. If you're going to write code, it's probably actually more convenient to do it the other way, but let's do it this way because it makes a little more intuitive sense. So the number 25. So how many 32s do we have in the number 25? 0. That's right. Oops, sorry. I should close the question here so that I can see the chat again. All right. Is that the answer already? Oh, very good. So we have 0 32s. Now we do have some 16s in there. So we are going to have a 16. So now what is 25 minus 16? So we've now accounted for 16 of the 25. So what's 25 minus 16? 9. That's right. You can tell who's going to be a computer engineer because we're like, yeah, I don't know, real numbers are not my thing. That's fine. All right, so we have 9 that we need left to account for. So, well, an 8 will certainly go in there nicely. So 9 minus 8. We have 1 left. So there's no 4s, there are no 2s, but there is a 1. So yes, good job in the chat. 0, 1, 1, 0, 0, 1. You could also work this problem from the other direction using things like the modulus operator. I'll let you think about how to do that. There we go. All right, so now we've kind of gone back to school and had to think about our place values of numbers again. You probably didn't come in here this morning thinking that you're going to be doing like grade 1 math, but it's grade 1 math with a completely different base representation, which means we need to think about it very differently. And now we actually understand what all those zeros and ones mean inside of a computer's memory, which also means when you walk through the core science building, sometimes you will start to get the jokes that the junior and senior class write on the whiteboards of the junior lab and the senior lab to each other. They had, there are some in-jokes and things that involved the ordinal values of numbers happening last year, and some of them might be binary as well. But in any place value system, we have a place which is a base to the 0, base to the 1, base to the 2, base to the 3, base to the 4, base to the 5. Whether that base is 10, which is what we're used to, or 5, or 20, or whether it is 2, which is what the computer uses. So the computer's memory stores bits, and those bits can be used to make a binary integer representation. So now do we see why it is called binary? Why is it binary? Because there's only 2 numbers, 0 and 1. So we have binary operators, have 2 operands. We also have a binary representation of things that only uses 2 values, 0 and 1. And there are other kinds of representations, and if you're interested in Python, we can see those. Like if I want to look at, well, what is the hexadecimal representation of the value 123? It says, oh, it's 0x1b. If I want to see what is the binary representation of the value 123, use the bin function. It says it's 11111011. What was the number we had a minute ago? 25. The binary representation of 25 is 11001, just like we found. So that's how the computer represents integers. And next, we'll see how we can put that together, or how we can use multiple integers to represent a floating point value. And then we'll be a long way along the ways to understanding how computers can represent things. So that is it for today, And so, yeah, I don't see a lot of questions coming in on the stream, so I'll just go ahead and close the chat. So have a lovely day, everybody.